Hello everyone! Today I'm going to show you a technique that we can use to precisely control the position of the vertex of a curve or a mesh. This will allow us to define parametrically a steel profile like an I-beam or a rail profile like we did in the previous video. As usual, let's start by opening Blender and creating a new scene. This time we are going to keep the default objects and apply a geometry node modifier to the default cube. To do that, we select the cube and in the modifier tab on the right we click Add Modifier and select the geometry node. Now we are ready to switch to the geometry node workspace. Now we are going to change the default spreadsheet editor for an image editor, so we can load and display a reference image that will guide us through our project. Now, if we press the N key while in the node editor, Blender will show us the right control panel, where in the Group tab we can define the control parameters that we will use to set the position of the vertex of a curve in order to turn it into our reference profile. As you can see, with the plus button we create a new parameter, then we set its type as float and rename it accordingly to our reference image. For each parameter that we create, we can also define a minimum value, a maximum value, and a default value. It's important to notice that after we have created and defined our parameter, even if we have set a default value, we still have to manually initialize it on the right. To create our curve, we start with a mesh line. This will allow us to precisely control the number of vertex in our curve, whereas if we start with a curved line, in order to set the number of control points, we will have to use our resample node. Now we create a new math node and we set its operation to multiply add, so we can use it to calculate the number of points that we will use to define our profile, or half of it to be precise. Since we define a control parameter n that we will use to set the number of segments in each of the filleted corners of our profile, and since the number of such corners is 5, we can say that the number of vertex that we need is 7 plus 5 times n. This is because we also have 2 spare vertex that are not filleted. This is equivalent to say that the number of vertex in half of our profile is 2, that is the number of single vertices, plus 5, that is the number of filleted vertex, times n plus 1, that is the number of vertex for each round corners. Now that we have done our math, we can connect the output of our math node to the count parameter of our mesh line node. Since in short order things are going to be very messy, we start by adding a new frame that we will use to segregate the nodes that we will use to define the vertex position of the first filleted corner. So, by pressing F2, we can rename it R1, then with Ctrl-C and Ctrl-V, we copy and paste the group input node, so we can minimize the number of connection lines that will go across our node tree. Now, after our mesh line node, we add a set position node that will set the position of the vertex in our mesh. To do that, we add a switch node, set its type to vertex, and connect its output to the position input of the set position node. To control the switch node, we add a new compare node and connect its output result to the switch parameter of the switch node. Now we add an input index node, change the type of the compare node from float to integer, and connect the index input to the a parameter of the compare node. Now we set the operation of the compare node to less than or equal and connect the n parameter of the input node to the b parameter of the compare node. This will allow the switch node to set the position of the vertices with an index less than or equal to n. That in our case will be the vertex that will define the first corner of our profile. Now we add a new combine XYZ node that we will use to set the center point of our rounded corner. So, using two math node, we set the x component to the b parameter divided by 2, that is half the width of our top flange, and we subtract r1, that is the radius of the first rounded corner. Now we set the y component of the center point to the eighth of our profile, that is defined by the input parameter h, and as before we subtract r1. Now we can connect the output socket of our combine XYZ node to the true input socket of our switch node. So when we set the input parameters to some reasonable value other than 0, we can see some results. Now we add a new math node, set the operation to radians, and set a value of 90 degrees that will define the amplitude of the first rounded corner. Now, as good practice, if we select our combine XYZ node and press F2, we can rename it center. So, in the future, we will know what it's meant to be. Now, if we divide our 90-degree angle by n using a new math node, we can compute the amplitude of each segment of our rounded corner. Now, we can use a new math node to multiply the index by the wedge amplitude of each segment in order to obtain the polar coordinate of each vertex of the rounded corner. Now, to convert the polar coordinate to a Cartesian coordinate, we use two math nodes with the operation sinus and cosinus, then multiply the result by the radius to obtain the x and the y component to feed to a new combine XYZ node. Now, using a new vector math node, we add the coordinate of this new point to the center point and connect the result to the true input socket of the switch node. In this way, we can start to see the results of our work, and so the first rounded corner of our profile is done. Now we can copy the frame and all its nodes with Ctrl+C and Ctrl+V, and then by pressing F2 we can rename it to R4. Now we can delete the math node that we used to define the center point of the first rounded corner, so we can make room to define the center point of the second rounded corner, that even if in our reference image is not rounded, we want to be rounded, so to generalize the profile of a generic I-beam section. But before doing that, we need to account for the nodes that we already set in the first rounded corner. So we add a math node to subtract from our index the number of vertex of the first rounded corner that we can compute with another math node set to multiply add, where the first parameter is n and the second and the third we set to 1, and as usual we rename the node by pressing F2. Now we need a second compare node and a Boolean math node to isolate the upper and lower bound of the indexes of the vertex that we want to set with this node. Now, since we want the next segment of the profile to be inclined, the angle of this rounded corner is no longer 90 degrees, but we need a new math node to subtract the inclination of the segment that we defined by the parameter alpha. Now we can drag the socket of the input parameter R4 to the multiply node after the sinus and cosinus nodes, so we can properly define the radius of this rounded corner. Now we need to swap the x and the y component to account for the different orientation of the second corner, and we also need to add a new math node to change the sign of the y component by multiplying by -1. Now we can connect the output of this switch node to the false input of the previous switch node. In this way we can daisy chain the two nodes. Now we still need to define the center point of our rounded corner, so we use a new set of math nodes. As we go along with this fancy math, we should see the results appear in D3D view. Since the results are not what I was expecting, it's a clear sign that I messed up something. Let's try and fix it. Here is the problem. This should be greater than or equal. Much better. As before, we select and copy the frame and all its nodes, then we rename it and we modify it to fit our needs. The first step is to account for the number of nodes that have already been set in the previous nodes. Then we need to set the new coordinates of the center point. This time we need a lot more than some fancy math, so we sketch the geometric problem to define the y component of the center point, so we can come out with the solution. As we can see on the sketch, these three triangles are similar and have one angle of 90 degrees, and the smallest angle is alpha. Now it's a good idea to create a new frame. As often in life, and more often in math problems, things appear harder than they actually are. Here we can take advantage of the fact that the vertical distance between the center of the second and the third rounded corner can be obtained as the sum of three quantities. The first and the third are quite straightforward to calculate, as the cosinus of the alpha angle times the radius of the rounded corners, whereas the second quantity is quite tricky, because it depends on the length of the segment between the second and the third rounded corner. But we only need to calculate the horizontal projection of this length, that we can call x. Then we can obtain the vertical component y as x times the tangent of the alpha angle. Now we can see that the horizontal projection can be obtained as the sum of the horizontal distance between the center of the second and the third rounded corner and the sum of the two radii times the sinus of the alpha angle. Now that we have figured out all the quantities involved, we can go on in calculating the center position of the third rounded corner. Now we have to take into account that the angle that describes the position of a point along our filleted corner doesn't start at 0, but at an angle of alpha. So we add a math node to add the starting angle and another math node to convert the alpha angle from degree to radians. Now we can finally convert our polar coordinates to our x and y component that we have to add to our center point. Now we don't need the annotation anymore, so we delete it and check if everything works as expected. And we need another math node to account for the fact that we only need half of the web thickness. We can change some of these values. Now, as before, we can copy these nodes and rename the frame to set the points of the next rounded corner. As usual, now we can change the number of vertex that we have already set and delete these nodes to make some room for the new ones. Here we need the beta angle. Now we can draw another sketch to come out with the vertical position of the center of this rounded corner. Lucky for us, this time the solution appears to be simpler. As before, we can obtain the y component as the x component times the beta tangent. And as before, to try and keep some order, we create a new layout and copy the input node group. Here we have named C the thickness of the base flange. But before starting with the math, we better rename this frame. We start with the thickness of the flange C. Then we need the cosinus of the beta angle times R2. We add the result to the C value. Now, to calculate the x projection of the inclined segment, we start with half the width of the base flange, W. Then we subtract the distance from the border, D, and half the web thickness, T. Furthermore, we subtract R2, and this time we add back R2 times the sinus of the beta angle. Now it's better to rename this node X before I lose track of it. And finally, we can multiply the tangent of the beta angle times our x projection. Now we add this value to the one that we already had, and so we are ready to connect the result to the y component of the center point of our root radius. As before, the x component of the center point is quite easy to obtain. Now we can connect the output of the switch node to the false input of the previous switch node. And then, once we have properly connected the x and y component of the rounded corner, we can start to see some results. Now that we have completed these steps, we can delete the sketched annotation that we used as a guide for solving our geometry problem. And as usual, we copy the frame. This time, since the next corner is not rounded, we can delete all nodes responsible for the rounded radius. And since we have only one vertex to set, after accounting for the number of vertex in the previous nodes, we only need the equal comparison for the index. Now, after all the math that we have been through in all the previous steps, calculating these vertex coordinates, it's a child's play. Now we can rename the frame with the F2 key so we don't lose track of all the bits and pieces of our node 3, and we are ready to connect the result to the previous switch node. Now, since the next corner is rounded, we can copy and rename the previous frame, change the number of previous vertices, set the x component of the center point, connect the correct radius to the multiply math nodes, and set the y component of the center point of the rounded corner. We daisy chain the last switch node, we reconnect the x and the y component of the radius, and we remember to set the amplitude of the angle to 90 degrees. And in the end, we can set the coordinates of the last vertex to y0 and half the flange width for the x component. Now that we have completed half of our profile, we can reuse the mirror node group that we created in the last video to complete the full profile. To copy a node group from another file, we can use the append command in the file menu. Select the file that contains the node group and then browse the node tree to select the group that we want to copy. Once we have done that, we can simply insert the node group as any other node from the Add Group menu. Now, if we select the Close option, we see that we forgot to convert the mesh into a curve. So, we do that by adding a meshed curve node. And finally, we get the results that we wanted. Now, we can use a fill curve node to check our profile, and If we fancy, we can change the parameters to turn the rail profile into a wide flange I-beam profile that we can extrude to build some structure, but I think that we will leave that for the next video. Bye bye!